Good morning, everyone. Welcome to the Build Your Simulation Mechanical IQ webinar today. Today we're going to be discussing working with single elements to understand simulation mechanical. I'm going to be one of the co-hosts today. My name is Dean Rose. I'm a customer support specialist here at Autodesk, and speaking with me today is going to be Marwan, and he is a customer support specialist in the Pittsburgh office. So we're kind of representing from almost coast to coast here. We have a lot of people joining the webinar today, and Marwan is going to be presenting. I'll be talking with him. And Marwan, if you want to go to the next slide.
All right. Oop. Here we go.
All right, we'll jump right into what we're going to be talking about today. It's going to be a fairly basic presentation, so I'll just warn everybody, if you're an advanced user, you may not see as much benefit as some of the people that may be new to the product or looking to learn a little bit about some of the functionality. I feel we can provide some value for everyone that attends, but I don't want to give the impression that we're going to be talking down to anybody. We're going to be investigating beam elements and some of the various material models that we have, response beyond yield. So these are some questions that we get quite a bit. What happens when we load a material beyond that yield point? How come my stresses are getting so high? It doesn't seem realistic. We're going to cover that a little bit. Then we're going to jump into plate elements and look at some of the results, component results versus magnitude, some of the plate display options that we get a lot of questions about here in support. And then lastly, we're going to cover the solid brick element. And we're going to look at a compression case and then do some reaction plots versus applied force, try to get some additional understanding about what's going on there. Again, we want to provide some value to everyone, showing how easy all this is, what kind of demonstrations you can use for troubleshooting. Here in support, it's something we look at when people are confused about things or don't understand, or sometimes we find defects. And looking at the very basic element level is sometimes the best way to do that. So I guess we'll go ahead and get started. Go ahead and go to the next slide, Marwan.
All right. This is just a generic slide here. So our models are going to be basically single element models, be it a plate, a beam, or a brick element. And of course, we're going to build those right inside of simulation mechanical, which some of you may or may have not done before. So I'm going to start that and bring up simulation mechanical here. This is just, I did file new and I gave it a name, so that's how you would start your own model, file new. And we're going to start with the beam element, which is a line element. So I'm going to go to draw line, and I'm going to uncheck use as construction and draw a line in part 1, just a single line starting from 0, 0, 0. And it's going to be 6 inches long in the X direction, like this. So if we do this now, here's our line here. And actually, as Dean mentioned, we're going to have various material models. So we're going to make 3 elements, not just 1 element. So I'm going to right click, go to select line, select this line, make a couple of copies of it, move over copy, copy. Total distance is going to be 8, 2 copies actually, and we're going to copy in the Y direction. So we get 3 lines, nothing too exciting. We're going to select this line and right click, edit attributes, make that part 2. This will be our part 3. Of course, since we're talking about nonlinear material models, we're going to change the analysis type to MES with nonlinear material models. I'm going to create a new design scenario. No. And here we go. Select all three here and change those to beam. I'm going to start off with them all being the same. Okay, well, it doesn't allow me to do them all together, so we'll do each one individually. The first one is going to be the default, which is isotropic. I'm going to go into the cross section, make that a beam of 0.25 inch radius, a round beam, and it will fill out the sectional properties. The second one is going to be also similar, except that the material model is not going to be isotropic, but rather von Mises with isotropic hardening, which is basically a bilinear material model. It's going to have the modulus of elasticity up to the yield point, and then it's going to have a different slope. Same cross section here.
And so, Marwan, when we set this up, we're actually going to look at the same boundary constraints, the same loading, and then we're going to be able to view how this is responding with the different material models.
Exactly, yes. And this is coming in just a minute here. So the last one is going to be von Mises curve with isotropic hardening. So it's going to have a curve behavior beyond yield. The material is all going to be A36. However, it's going to have slightly different properties depending on the material model. For just isotropic, it only needs the modulus of elasticity and the Poisson's ratio. The yield is not going to do anything here. For the von Mises with isotropic hardening, it's going to have the strain hardening modulus, which is the second slope. And for the von Mises curve, I'll show you that real quick. When you select that same material, and if I click on Edit Properties, it'll show us the stress versus strain curve. Let's save that real quick. I'm going to go Selection, select Vertices. I'm going to select the bottom vertices and fully constrain those. And then here I'm going to select, let's see, where's my beam? That's going to be a force. I'm going to apply a force to all three of them, the same force, add nodal force in the x direction. That's going to be 10,000 pounds in the x direction, just basically stretching it out. Everything else is going to be the default load curve. It's a linear load curve, and analysis parameters, which is going to go with the defaults. And let's go ahead and run the simulation. This should take a couple of seconds to run. Again, we only have 3 elements in this entire model.
And so this highlights a little bit about how simple this model is to set up, and then we can quickly view the results and really see something that we may not be able to see in a large model that contains hundreds of thousands of elements. So just a good way to troubleshoot.
Exactly. In 5 seconds here, we ran 3 different material models. If this was your actual model, it might still actually be checking the model. And now we have results that we can look at. So again, this first one here is isotropic. This is the isotropic hardening, and this is the curve, the third one. So what we're going to look at here, let's look at the displacement in the x direction. Actually, I'm going to select all 3 nodes, right-click, add probe to selection, so we can see the values. Zoom in. So obviously, the isotropic displaced the least amount, 0.01. The von Mises with isotropic hardening, 0.94 almost, and the von Mises curve, 0.61 inches. To look a little further, I'm going to select this node, right click, and go to graph values. And this is the displacement versus time, very linear. Go back here, select the von Mises with isotropic hardening, do the same thing. Graph values, and you can see that it has a linear up to yield and then a second linear portion beyond yield. That's again the displacement versus time, or load, if you will, because the load is a function of time. And last but not least, right click, graph value, and here we can see that it's similar to the von Mises with isotropic hardening, except that you can see that there's a curvature here to this portion of the plot, and that's because the material properties are curved, stress versus strain curve. So we can clearly detect the different behavior based on the material model. Another way to look at this setup here is to go back, and if I copy this design scenario, and instead of having a force, now of course if I looked at the stress, the axial stress in these, they're all going to be the same because it is the force divided by the area. We're not going to see any difference in the stress. Now if I delete the force here, and instead of a force, I select these nodes and I add a nodal prescribed displacement of 1 inch in the x direction. Just a little variation on this model that will also give us something interesting to look at. Now the displacement, of course, is 1 inch, the same for all three of them. If I look at the beam and truss axial stress, actually let's also add probes here. You see that the value for the linear, the isotropic, is much higher than the other two. The other two are much lower. They're very close to each other. The von Mises curve is a bit higher, but let's plot these. So the linear is obviously linear. You don't see any change when it hits, goes beyond yield. So it doesn't know that it went beyond yield at 36,000, which is way down here. You're not going to see that in the linear material model. There's no yielding. This one, of course, will show you the yield. So the stress is going to go up to 36,000, and beyond that, it's another straight line here. That's the von Mises with isotropic hardening. Now the von Mises curve will actually have a curve beyond yield, like this.
And I think that's really good, Marwan, because it demonstrates one of the principles. If you're loading a structure beyond the yield point, you may be doing a linear material model, and if you're getting stresses that are higher than that, that's when you might want to switch to the nonlinear material model, correct?
That's correct. If you are interested in seeing what happens beyond yield, because in a lot of cases, you just don't want to be there. You don't want the model to yield. So a linear would be enough. It tells you it went beyond yield. The results are no longer accurate, but you don't care to see accurate results beyond yield because you want to change things so that you don't get to that point. So it depends. You may or may not want to go to a nonlinear material model. Depends on what you want to see. I mean, if you want to see what it does beyond yield, then yes, definitely you'll want to go to a nonlinear material model, because otherwise, as you saw here, they just don't make sense. These are the results that make sense, either this or the von Mises with isotropic hardening. You clearly see the yield point and what happens realistically beyond yield, rather than that straight line that goes way up into the millions of psi.
Perfect. While we're here, I think we might kick off our first poll of the day. And I'll go ahead and launch that. Let Marwan regroup here while we get ready for our next model. And this one has to do with what level of simulation mechanical user are you? We've got quite a few different people on this call, probably some resellers, some customers. I think we probably even have some Autodesk employees that are just sitting in and watching and learning a little bit more about the program. And I know we probably have some Algor users. And if you're not familiar with what Algor is, then you're probably in the rookie category. And so it looks like getting a lot of votes coming in. Feel free to select your choice. It looks like we've got a lot of new users on the call. So a lot of rookie category, avid users. We've got some of those. So this is probably a really good webinar for you guys, highlighting some of the basic functionality to help build a strong foundation for doing the FEA. We'll go ahead and close the poll. And it looks like 41%. Only 23% are the wily veterans from the Algor days, so I think it's really good. Glad to have everybody on the call. So next we'll jump into plate elements, right, Marwan?
That's correct. So what I'm going to do is, again, something very simple, which is a 1 inch by 1 inch plate element. Actually, I wanted that to be linear, not linear. So to do that, it's going to be really very simple. I'm going to go to mesh, and I'm going to do a 4-point rectangular mesh, and it's just going to be a 1 by 1. So we're going to start from 0, 0, 0 in the corner, hit enter. We're going to use relative. We're going to go 1 in the x direction, enter, 1 in the y direction, enter, -1 in the x direction, enter, and apply. And here's our element. It's not shaded because it still doesn't know what element type it is. Once I change that to plate, it's going to get shaded. So here's my 1 inch by 1 inch element under element definition. So this is in the xy plane at z equal to 0. So if I select a vertex here, any one of them, and inquire, it's at z equal to 0. And you'll see why I mentioned that. Now when I go into my element definition, I need to specify the thickness. I'm going to make that 1/8 of an inch thick. And the element normal point by default is 0, 0, 0, which makes it in the same plane as the element itself, which is not really a good idea. What the element normal point does, it defines which side is the top, which side is the bottom. So I'm going to make that element normal point 0, 0, -1 in the z direction, which makes really this side down here the bottom. No, actually, it's -1. So and the negative z would be the bottom, and the positive z, so this would be the bottom, this would be the top of the element. And you'll see that when we look at the results. So here's our one element model. Again, the loading and constraints are going to be simple. Before I do that, I'm going to go in and set a material. It could really be any material for our purposes, so let's stick with A36 here. It's not going to make a difference. Select these two nodes, add constraints, make those fully fixed. Plate elements are, by the way, 5 degree of freedom elements. They have the 3 translations and 2 rotations. The rotation in this case about the z-axis is not available. The drilling degree of freedom is not available. And in this model, I'm going to have 3 load cases. The first load case is going to be, I'm going to add, they're all going to be forces, by the way, nodal forces. We're going to add 10 pounds, or I'm not sure how many pounds let's make that more. Let's make that 100 pounds in the Y direction. So that's basically simple tension.
No mercy, Marwan. Load it up.
Load it up. With those two nodes still selected, I can right click and add another nodal force, and that's going to be 100 pounds on each of them, by the way. So the total would be 200. And that's going to be in the Z direction. That's going to be pure bending. And for load case number 2, pure bending. And right click, add nodal forces again, 100. But in this case, it's going to be a combination of bending and tension. So let's make that a custom. It's going to be Z1. So it's going to be up, and Y -1. And that's going to be load case number 3. So if we zoom in, load case number 1, this guy here, those two forces, pure tension. This is pure bending. This is a combination of both. So let's go ahead and run the analysis.
And again, this is an area we get a lot of questions about. Marwan's going to cover some of the plate display options that we have, and it's an area of concern for customers when they're looking at results and just helping understand. So hopefully, if you have any questions, this will answer those.
Okay, so this is load case 1, which is the retention, and this is displacement. We're not really looking for the displacement. I'm going to look at the stresses. This is the von Mises stress here. The minimum and maximum are on either end. And what we really want to look at, though, is the stress tensor in the Y direction, is the Y component. 1600, that's based on the area. So it's, what, 200 divided by 1/8, 1600. And if I go to results, contours, settings, plate options, so that's again under still results, contours, settings, plate/shell options. That will allow me to look at the total stress, the bending stress, and the membrane stress, which is the total is the sum of the bending and the membrane. The bending is due to bending, and the membrane is just the simple tension. So let's do this. Let's select these two nodes, or actually we can just select one of them. Doesn't matter, or one of those here. Right click, inquire results. There's my inquire results here. So my total is 1600. My bending is 0. There is no bending stress here. And it's all membrane. If I look at my load case number 2, which is the total is this 63,000, the bending is all of it. The membrane is 0, because this is, again, totally in bending. If I go to, and we'll come back to this here in a second. If I go to my third load case, this is my total, 43,431. Part of it is bending, and part of it is membrane. I'm going to go back here to load case number 2, which is fully bending, and show you this both sides, top side or bottom side. Now, the bottom side is this side here, and the top side is this side here. And you can see the colors changing. So this color by two-sided display, whichever side is shown. In this case, the top side is shown, which is in compression because my force is like this. So this is in compression. That's why it's negative. It's blue. If I flip this and look at the bottom, it's red because this side is in tension. That's what happens when you're looking on both sides. Whichever side is displayed, the contour is going to be colored based on the displayed side. If I do top side only, which is again going to be in compression, you can see that all the numbers are negative because the top side is always in compression, and it doesn't matter if I change the view, the contours are not going to change based on the view because it's always based on the top side. Similarly, if I change to bottom, it's all going to be in tension, and it doesn't matter if I change the view, the colors won't change. And if I go back to both, this is the top, it's in compression. This is the bottom, it's in tension. Again, the top and bottom is decided based on the element normal point, which in my case was in the negative z, -1, which makes this side the bottom and this side the top. And if I go to load case number 3, which has a combination of membrane and bending, and if I select the node, right click and inquire results, if I look at the bending, let me go to bending, the top is -44,562, the bottom is the same value except it's the opposite sign, it's positive. So they're both the same absolute value but different signs, positive and negative. The membrane is going to be the same for both of them. It's negative, so it's compression, right? And the total for one side, in both cases, is going to be bending plus membrane. So the membrane is the constant portion of it, and the bending is the one that flips signs. It's the same value, but flips signs between top and bottom. Does that make sense to you, Dean?
That makes a lot of sense. I've gotten a few customers asking, well, when I switch to total, what does that encompass? And being able to see that visually here should really help develop some understanding about what's going on. And I think yesterday when we were working on this, we were looking at the von Mises stress and some of the consequences of viewing that related to the tensors. Maybe we could show some of that information.
Right now we are looking at the y tensor. If you look at other tensors like the XX or well, the YY is going to be more, more easily correlated to our loads.
Yep.
The von Mises, since it's an absolute value, it's going to be a little harder to interpret here than this. But still, the bending and the total, here it's the total, the bending is 39,760 and the membrane is 1,000. So if you add 1,000 to this, it's going to be on one side 4760 and the other side 38 because we're subtracting the bending.
And I also wanted to highlight here something that some of the users may not be aware of. You're using this inquire results dialog here, which allows you to easily switch from, say, von Mises to the tensor components, switch between load cases, and there's no need to close and reopen that results dialog. So this could save some time for your workflow.
Yeah, so when you're in von Mises and right-click, we can switch between the different types of stress. We can go to stress tensor, and once we're in stress tensor, we can switch between directions. So you don't have to close this, you don't have to reselect. The only way you're going to lose your selection is if you left click somewhere here, then you lose your selection. And you have to select your node again.
So yeah, I think that's really cool to help people that are giving demonstrations or just help them post-process the results a lot faster.
Yeah, excellent point.
All right. Well, let's go ahead and launch another poll here. I'm going to kick this off while Marwan's getting set up for demonstrating the next part. And we've been covering building models and doing this manually. Sometimes users that we talk to aren't familiar with this, so I was just curious if people are using this functionality, like what we've been demonstrating here. Sometimes maybe this is something that doesn't provide a lot of value for you. Maybe some of you are not aware this was possible. And then some of you may just be importing CAD geometry that you're building in another platform, so you may not be using this at all. So feel free to chime in there. And being able to manually build things is kind of an advanced tool that you can use. It's usually best suited for simple models, circles, cylinders, squares, things like that. Things that we're demonstrating here are perfect for it. So,
Yeah, I mean, and theoretically, you can build any model, no matter how complicated it is, manually inside of Simulation Mechanical, theoretically, but practically you really can't. I mean, you can build some neat 3D models, by hand, but you get to a point where it practically becomes impossible. Because at the end, it is a bunch of lines, and theoretically you can build anything you want, but once you get to really complicated shapes and so on, it just either it doesn't, practically becomes impossible, or why would you ever do that? The question is, why wouldn't you build it in CAD and import it? And the question is, yeah, you would build it in CAD and import it. You wouldn't want to build it by hand. There's no reason.
definitely. And it looks like we've got majority of the users that are importing CAD geometry. So this might provide some value if you're looking to do some troubleshooting or maybe just build a very simplified model of what you're looking to analyze. So perfect.
All right. I just copied this design scenario, the plate design scenario, and created a new one, and I called it brick. It's still the same plate model. I can actually even call that brick. It's not going to complain, right? But of course, it doesn't make a valid brick element. I'm going to select all the vertices here and delete the loads and constraints. And then I'm going to select these lines, and in order to make a brick element, I'm going to right click, go to move or copy, and that's just one way of building a brick element. There's more ways. Copy, join, one, and the Z direction, and there we go. We created our brick element. And with this brick element, what we're going to go to element definition. Since we changed the element type, it's always good to go down the list here, go to element definition. You don't have to change anything, you can hit OK. And for material, same thing, just verify that, hit OK. For this, we're going to have a couple of load cases. Both of them are going to have the nodes down here, the vertices, all four of them fully fixed. Select these four vertices and and load case 1, we're going to add nodal forces -10 and the Z direction for each one of those nodes. So the total would be 40. And in load case 2, it's going to be a lateral force, again 10 pounds, but that's going to be in the y direction, and we'll make that load case 2. So we have two load cases, load case 1, simple compression, and basically shear for load case 2. Let's go ahead and run the simulation and take a look at some of the results. In this case, we're not going to look at stresses like we did with the plate element. We're actually going to look at reaction forces. So, you might be wondering, why do we have 3 load cases? Well, that's because I copied it from the previous one, and if I go to the third one, we're going to have 0 results because we didn't create any loads in the third load case, which is fine. We can keep that. It doesn't hurt us. So load case 1 again is the compression, and if I go to reactions, reaction force, magnitude, and select my 4 nodes down here, right click, inquire results, and I look at the sum, I get 41.635, let's say. And you might look at that and say, well, I only applied 40 pounds. Why am I getting 41.6? That seems, too much. Well, it is. And that's because I'm looking at the magnitude here. My forces are applied in the z direction, and they will generate some reactions in the x and y, not only in the z. So really, if I want to see my 40 pounds that I applied, I need to be looking not at the magnitude, but rather at the z, and that's exactly 40. And if I look at the x, that's basically 0, and at the y, that's also basically 0. Then you come back and say, well, if they're 0, why did they change my magnitude? Well, because at each node, they cancel out, the x and y. If you sum them up, they cancel out, but they are not actually 0. They're basically 2 pounds, but -2, and +2, and +2. So they contribute to the magnitude, but if you look at them individually in the x or y, their sum would cancel out to 0, but they would contribute to the magnitude, and that's why we get 41.63. And if I look purely at the z, I'm going to get exactly 40, 10 at each node, -10, that is.
And that's a great point, Marwan. A lot of people get tripped up by that. And I think the load case 2 that you've set up helps demonstrate that a little more clearly as well.
So if you go to load case 2, and that's where I have this kind of shearing force in the y direction. And again, if I look at the magnitude and the sum for all these 4, now I'm getting 89.95 basically, even though I know my total is 40 pounds. Well, that's your 40 right here in the y direction, exactly 40. But I still have in the x, you have the 2.37. Again, they add up to 0, but they're going to contribute to the magnitude because and the z is also basically 20. It's different, of course, from the x. The x is small, it's 2, but the z is 20 because of that moment. And
this is good because it demonstrates something with a single element that you can easily see. You can query each of those nodes, get a really good understanding. You can actually go through and add the components up. doing a sum of squares and taking the square root and getting that magnitude value. Something that would be very challenging to do in, say, a large model with, 1,000 elements that may be bending response, and some of those components may not be canceling each other out depending on how the load is applied and how the structure is responding. So uh, this is a great tool to help understand that if you're looking to learn how to use the software, learn some of the results that are available. So yeah, really good stuff, Marwan.
Yeah, absolutely, Dean, because there's a clear cause and effect here in this model. You only have four nodes that you want to, do calculations on, and you can very, easily do hand calculations and get matching 100% numbers, whereas if you have a big model, you don't know what's going on. I mean, you know in general what's going on, but it's much harder to see the picture clearly as you would here. And I know we basically oversimplified with one element. I mean, this could have been, 20 elements cube. This cube could have been 20 elements and it'll do the same thing, right? It's still going to be easy, but one element is, of course, easier. But it doesn't necessarily mean that you have to have a one element model to do what we're doing here. It could be, a handful of elements and still be very, very easy, just the same. So yeah, for the magnitude, you can look at each node individually, and if you do the numbers, this square root of the sum of squares, they will all make sense. You will get the numbers that you do expect. In this case, you take the 2.37, the 20, and the 10 pounds, and you square those and you sum them up, and you're going to get what you're getting out of the inquire results window here in simulation mechanical as far as the magnitude and of course the individual directions.
Perfect. Well, I think we've covered the three models that we've set out to. If you want to jump back to the slide deck, Marwan, we'll start to close this up, head towards the end, and we'll allow some people to ask questions if they have any. So this is beam element. Do you want to fast forward here, and we'll get to the conclusion and just kind of highlight some of the things that we've done. So we did the plate elements, looked at some of the display options, top, bottom, and both. A very common question that we get from a lot of people. We've demonstrated the solid element, how to capture those reaction forces, some of the consequences of the magnitude results versus the component level results. And here we're just trying to view and understand the results. And then lastly, we want to make sure that we're providing some value here, ensuring you know that using single elements has a very fast setup. Applying boundary constraints and loading is very simple, easy to troubleshoot. You can actually go through and do hand calculations and verify some of the output, so it's very easily understood. And then it's a valuable learning tool if you're looking to get started in simulation mechanical, or you're looking to do maybe some different type analyses using different elements. This is a great way to gain some understanding. And then lastly, being able to understand this, like Marwan went through some of these features, it's a great, strong foundation to build upon. If there's some of these topics that you just aren't familiar with, maybe something new, being able to understand those will help you apply those principles towards the larger models. So a really great place to start.
Absolutely. We'll see if we have any questions here. And
while we're waiting for questions, we have If you want to download the slide deck or the archive of the models that Marwan was demonstrating, it will be available in the link below on this slide. And then while we're waiting to see if anybody asks questions, we just had a Service Pack 1 that was released for Simulation Mechanical 2016. And we'll go ahead and see if anybody has installed this. If you're a Simulation Mechanical 2016 user, it does provide some fixes and some updates. And some of you may not be aware that we've released it. The link is on the forums. And I will also post a link here to a download article in the chat window. And so that's a great place you can go. Check that out. Want to keep everybody current. I won't ask Marwan if he's updated to the latest service pack.
Well, I keep both actually. I keep one version on one machine that is the latest and one that is not, just so I can compare. One other thing about the archive file that's going to be posted, like Dean said, this presentation will be up on a box folder that you can download along with the archive file. It's just going to be one archive file. These are different design scenarios in the archive file. And in the one that we're going to upload, I actually have one more design scenario for a truss element. It's going to be an MES analysis type, so it's going to be a non-linear truss. That's basically an extra model I threw in there, and the material model for the truss element is a curve, and that what that allows you to do is to have a different behavior in compression for that truss element than you do in tension. So if you have some kind of spring that has a different spring constant in compression than it does in tension, you can use the curve. The model I have is simple, where it's just one basically slope in the negative and one slope in the positive, but that is a table, and you can have any stress versus strain profile that you want, not just necessarily two straight lines, two slopes. You can have multiple slopes. It's a piecewise linear curve that you can have in there. And I apply a prescribed displacement, I think, of 0.1 inches, and you'll see that the reaction force is going to be different depending on whether it's in compression or in tension.
Awesome. That's Marwan. He's always throwing in extra value for the customers, so feel free to check that out. And then we also have another webinar coming up. That's going to be with our Simulation Mechanical PM, Suwalp, and he's going to be covering some of the functionality in Simulation Mechanical, and I believe that's on October 7th.
Okay.
And I'm not seeing any questions coming in. Looks like we've blown everybody's minds. And if you don't have any additional thoughts, Marwan, I think we'll go ahead and wrap this up. Give people back 10 minutes.
All right, that's all I had.
All right, awesome. Thanks, Marwan. Thanks, everybody, for coming today.